Okay, let's get started. So before we start, today we're going to finish up the unit on machine learning and really going to be kind of bringing to a close what we've been doing on machine learning so far. Before we start, I wanted to mention a few administrative things. First of all, the homework's due on Thursday, so next class. You do have those late days, but remember you only have 5, I think, was there? Oh, that's how many, right? 5 total. So use them wisely. There will be extra office hours because of the homework being due on Thursday. So I actually just wanted to, before scheduling those, and I'll post an email, I'll send out an email shortly, but before scheduling them officially, I wanted to ask, can anyone not make the time that would want to come, cannot make the time tomorrow between 2 and 3:30? Just by a show of hands, can anyone not make that time who would want to come? Okay, so they'll probably be tomorrow between 2 and 3:30. So by all means, it's in the same office as the normal office hours, but just a new time. And we'll do that repeatedly whenever we have a homework due, because I think that's when everyone somehow all of a sudden wants to come to office hours. The other thing is the project. So I was hoping I can actually have that out by this morning, but it's not quite ready yet. So I was going to have it by the end of today, the day today. But it'll be a brief description about the project and the proposal and what those two things both entail in a little bit more detail. The proposal is going to be due next Thursday. And it's fairly short, a 500-word proposal. It can be less than that if you want to. Basically, I just want to have some idea about what you're thinking of doing and what your references are, what you might be looking at, what kind of work you might be doing for this. For that, if you want to come talk to me on office hours about potential proposals, there's a long list of things you can do. So by all means, come to office hours. Probably not tomorrow, because I think people will be mainly thinking about the homework, but come to office hours next Monday then. And again, I'll send out an email announcing both these things, both the project guidelines being online today, and then also the extra office hours tomorrow. So are there any questions about those two things? The proposal itself, remember, you should be working in teams of 2, so you'll also want to at least start thinking about who you might work on this project with. But the scope of the project will also depend on whether you're in the 8:30 or the 6:30. So as much as possible, it probably will be a little bit easier if you work with someone in the same level group as you. You don't have to. You could do a project with someone in the other level, but you just might have to do a little bit more than the other person, and we have to sort of figure out how that works. So if that is an issue, come talk to me. But yeah, is the question back there? The hope is that you can do it with someone. So if there's someone that might have sort of similar interests, that would be the hope. Part of the point of the project is kind of work with someone else and do some collaborative work. If there are extenuating circumstances why that doesn't work for you, like you're just not going to be around very much toward the end of the semester or something like that, then let me know. That's fine. But hopefully you'll do it in pairs. That would be the ideal situation.
And so what's the time for the office hour next Monday?
It's the same as always. What's posted on the website, standard ones is 2 to 3 on Monday.
Oh.
Those are the standard, everyone, those are on the website. Those are the standard office hours, yeah. Every week. Okay, I think that was all I had to announce. Oh, one more thing. There today from 3 to 4 in Gates 6115, there's going to be a panel for many faculty in computer science, including myself, talking about the role of computer science in sustainability broadly. I mean, my focus is typically on energy, but it's going to be a panel of 4 faculty that all sort of worked on different aspects of sustainability. So if you're interested in that, please do come by. 6115, yeah, Gates. And if you're in CS, you should get an email about it. If you're not in CS and want to get future announcements of the seminar, it's the kickoff of a seminar series that we're running on topics in sustainability, broadly speaking. But if you want to learn more about that, then let me know, and I can get you on the list to get further seminar announcements. So might be of interest for some that are interested in this topic. Okay, so let's finish up what we're doing about the machine learning component of the course, really. Today we're going to finish up on this, which is going to be really about talking about ways of reporting errors. So once you have run your machine learning algorithm, maybe you use a test set, a validation set, you do everything right, you obey this procedure. When you actually evaluate performance now, how do you go about reporting that number? And what is that number that you actually report? And should you put, some error bars around that number? And how should you compute those error bars? That's what we're going to talk about today. And at least for the first bit of today. We'll then talk about an application of these kind of techniques. And this is, I'll be brief with this. What I want to do here is highlight even the fact that there are lots of potential applications for these things. And I'm going to talk about one particular project I've worked on in the past, which is work on predicting monthly energy bills given features of homes. So another application, right? We've been talking about predicting maybe demand for a whole region, like the whole Duquesne Light region of the state. But what about predicting just for an individual building, how much an individual building is going to consume, say, for a whole month? And we actually did a very nice little bit of work on that using some data that we got from a utility. So we got building by building energy bills from a utility, and we used a lot of machine learning techniques to predict how much we think they would consume given features of these buildings. And I'll talk a little bit about sort of the motivation for why that might be an interesting thing to do, and hopefully just give you more experience seeing applications of machine learning and how these techniques can apply to a domain like energy. That's the goal there. And then hopefully, if we have time, we'll jump into the second unit of the course, which is really about the physical electricity systems. So how do we, remember, the high level, I think, was that if we want to talk about energy and electricity in particular, then there are some things that are very hard to predict, right? Like, what the demand will be tomorrow, because it depends on people and all these kind of factors, where we can use machine learning to build these models. If you have a situation where, on the other hand, you're kind of trying to think about a physical system, right? Just like, if I turn on all these generators, how will power flow through my grid, right? There, you could use machine learning. You could, run a lot of examples, turn things on and off, and figure out what's going on. But we really have this whole wealth of knowledge about the physics of electricity that we should draw upon there. It would be kind of silly to start from absolute scratch and try to build these models when we really know how the physics of electricity work. And so the second unit of this course is much more about that physical side of things. How are we going to actually take these physical systems and understand what they do when we turn certain things on or off? That's the idea here. And in this, we'll talk about today, hopefully get to some basics of AC and DC circuits. Or actually DC and AC in that order, those kind of circuits. So actually, as a brief question now, who here has background in electricity? So you've taken a course on AC or DC circuits, by a show of hands. Okay, so a good sort of complement to people that had the machine learning skills, I guess, though. That's great. All right, but let's jump in now to the end of our machine learning section here, which is about reporting results. So remember, we had this cross-validation procedure, which was we don't want to let our test set kind of influence any of our selection of parameters, right? And that includes things like the lambda parameter for regularization, or the number of features we might pick, or the choice of kernel, etc. These are all things that are choices of the algorithm, and we don't want to let the test set affect that in any way. So what we do is we break the data into training and testing sets, then split training again into training and cross-validation, use cross-validation to determine all our parameters and hyperparameters, these kind of things. And then finally, at the very, very end, we go and we test our performance on the test set. And that's our basic procedure. And that's kind of the way we make sure that this number here on the test set really is an accurate estimate of what we expect our performance to be, and it's not unfairly advantaged by some sort of tricks we've played. So does this make sense to everyone, sort of why we follow this process here? Are there any questions about this? Okay. It'll be on the next homework too, so you'll go through it in a lot more detail, I'm sure, when the next assignment is out. There's a slight variation on this, which you might come across a lot, which is called k-fold cross-validation. And the idea here is that our sort of split that we picked, 70-30, was kind of a little bit arbitrary, right? I mean, I just sort of threw that number out there. It's a very common number just because it sort of gives you a lot of data for tests for training, but still, you know, a good amount for testing. But it's pretty arbitrary, that number. And k-fold cross-validation tries to do something a little bit more disciplined in a way that lets you, in some sense, exploit more of the data. So the basic idea is the following. And I'm calling it cross-validation here, but really it can be used either for cross-validation or for the training testing split. It just goes with the name k-fold cross-validation usually. And the idea here is that when we pick only 30% of the test set, we're kind of, I mean, we might just get kind of unlucky when we do that, right? We might just pick a bad 30%, say, and we're kind of locked into that choice. And we're not really testing, for example, on all the data. You could repeat this a lot of times also, I should add. You could sort of select many different training sets, repeat the whole experiment many different times. But another common strategy is what's called k-fold cross-validation. The basic idea here is you divide your data into k different subsets, where k maybe is 5 or 10 or something like that. So you take all your data, all the data you have, this is before, say, any training or testing splits, or it could just be the training split after you sort of split out the first test set, but you can do it in either context here. And you split it up into 5, say, or in general k, different equal size blocks. Those should be equal size. I'm bad at drawing that. And then the idea is we're going to treat all but one of these as the training as the training set. And we treat the one held out one as the testing or validation set, depending on our context. Right? And then we repeat this process, now treating this one as the testing or validation set. And then this one, and everything else as the training set. And then, so you do this then k different times. And what this lets you do is this lets you use, in some sense, all your data at some point for testing, right? Because at some point, every section here was used as either the test set or the validation set. And so in some sense, you were using all your data to pick the parameters and to evaluate the performance of the method on it. But you're doing it in a way that kind of divides things up in a way where each time you still have this breakdown of testing and training. So we won't talk about this too much. It's just a term you might see a lot. People might mention k-fold cross-validation, and you should just sort of know what that means. So basically, it's a systematic way of building different training and testing sets, or training and cross-validation sets. And in the extreme case, this leads to a technique called leave one out cross-validation. And this is when k is equal to m. I probably shouldn't use k here, because k I'm using as the number of features that we always use, but it's just kind of the name people always call it. It's always called k-fold cross-validation, so apologies for that, but this is sort of the name of it. Anyway, in the extreme case, you essentially choose your holdout, or you divide the training set up into elements of size 1, right? Where you train on all the examples except one, and you test on the one held out example. And this is kind of the extreme of that, right? Where you're using kind of as much data as you possibly can to learn about that one last example, but still doing it in a way that kind of preserves the fact that you're not training on this one last example. And as you might imagine, this can be pretty computationally intensive if you for a lot of algorithms, right? Because you have to get sort of a prediction on every single example in this validation or test set, you need to train the whole algorithm on everything but that one example and pick that one example, and then do that m different times. So this can be kind of computationally expensive, but it also can be sort of very powerful in terms of you're using the most data you possibly could, right? Because a big idea for this in general is that we want to use a fairly large training set here to make a prediction on this one held out example, or many held out examples in the case of k-fold cross-validation. So these terms, they're not too important here. We're not going to really use these techniques too much in this class, but they're just good to know these terms and what they mean. When you hear the term k-fold cross-validation or you hear the term leave one out cross-validation, it's good to know what that means and how that relates to this training and testing splits. All right, so is that, any questions on this? Okay, so let's jump into the last bit then, which is now, remember this last bit here, we just said, well, evaluate the performance on the test set and report that. You write it in a paper. So what number do you actually put in your paper? That's the big question, right? And how should you report that result in your paper? If you get a classification task and you have, say, 80% accuracy on this test set, how should you report that? If you only have a couple data points or a small amount of data, you might sort of, in your test set, say, you might have the intuition that you're kind of less sure about that number because you don't have as many examples to test on. But you might get, say, 5 examples perfectly right, but are you really sure that you have the 100% accuracy there? How should you report those kind of results? And the same goes for regression, too. You know, if you report error on 5 different examples, how should you actually go about, you average your error or your loss function over 5 different examples, how should you actually report that? And that's what we're going to talk about here. And it's also something that is often not ever taught, and people do it wrong a lot. And so it's sort of good. There's very, very simple ways of doing it. It's a sort of basic statistics, but it's good. And in fact, it's kind of even a little wrong what we're doing here, and I'll point out where it's wrong and why it's wrong, but it's a very good approximation to what you want to do almost always. And so they can be sort of a very good rule of thumb for how you how you report results. Okay, so the important thing to notice here is that when we're talking about reporting performance in an algorithm, there really are 2 different questions we might want to ask. And the reason why this can be confusing sometimes is that people often kind of confuse these 2 things. Or sorry, there are the 2 things here. The next slide is the 2 things. This is just sort of a motivating slide. So we want to report our errors. And if we just report our test error, this is kind of what I was saying before. If we just report our test error, it doesn't really give us a sense of how confident we are in that prediction or what those predictions are like, right? So if we just report, say we have a regression task, and we report that our mean squared error was 1, in whatever units that y is in. Well, we don't really have any notion of how confident we are in that prediction, right? So if we have a test set of size 1,000, where we're predicting this on 1,000 examples, intuitively, right, this should mean that, well, we should be more certain that 1 is kind of a reasonable estimate of our error here if we just have a test set of size 10 or even smaller than that, right? So just reporting the mean squared error being 1 doesn't really capture how confident we are. And the second sort of issue, which is a little bit different here, is that we don't get a sense either of the variance of these predictions. So it could be that we're getting say we have a test set of size 1,000. It could be that we're getting all of them almost exactly right, like with error 0.001 or something like this. And we're just getting one of these examples horribly wrong. And again, just reporting the average of 1 does not capture the fact of explaining what our variance in these predictions really is. And so that can also be an issue. We don't get a sense of sort of, well, are you getting some really right perfectly and others just completely wrong? Or what does this really look like in some sense, these predictions? How far are they from the true value? So for both these reasons, you might think that just predicting the mean average error might not be the best idea. But we kind of want to do that too. We want to predict, have a single number that sort of quantifies the performance of our algorithm. So how can we go about actually describing this mean performance and getting some estimate of how good it actually is? So remember, our setting is, in the test set, we have a number. So remember, we defined our testing set as xi prime and yi prime, where I here went from 1 to m prime. So I just use primes to denote the testing set and just leave them off for the training set. Right? And remember, for our testing set, we have both the true labels, and then we also have our predictions, which I'm calling yi prime, because it's the test set prediction, and then hat. So use hat to denote predictions. And these things really capture the two things I was getting to on the previous slide. So first of all, what does this distribution of errors look like? Remember, I'm not talking about the actual loss function at all here. There's no loss. I'm just talking about if we graph, for example, plot a histogram of our errors, not absolute value there, but just yi prime hat minus yi prime, this being 0, say. So hopefully on average, for a regression task, we would predict correctly on average, but maybe there's some examples where we do badly over here, and there's going to be some distribution of what these things look like. That's supposed to be centered, or at least ideally it could be centered. So that's question 1. What does this look like? Maybe it looks like this, sort of a nice Gaussian distribution if you've seen these before. It could also say maybe, by happenstance, we have a big bunch of examples out here that we're getting, and maybe over on this side too. So we have a bunch of examples that we're sort of have really high error on. This is somehow qualitatively different than if we just had maybe the same mean error or same average loss, but these were more clustered in the center somehow. So that's the first question. What does this distribution look like? The second question then is, if we do want to report some average loss. So remember, we're evaluating and optimizing based on this loss function. And so we might want to therefore report, well, what's the average loss? Again, not on our training set, but on our test set. So if we average over all m prime examples, summing up the losses, what is that loss? And how should we go about reporting that? So these are the kind of, and importantly, how confident are we in that value, where our confidence should in some sense depend on the number of examples that we've seen. So these are the kind of the two things that we might want to think about here. So to introduce this, I'm going to introduce a little bit of probability notation. Hopefully you've seen most of this before. It's very, very basic here, probability. In fact, it's not even really, I wouldn't even really call it probability. It's just some very simple definitions here. But essentially, I'm going to use z to denote a random variable. So who here has had some probability before or done some work in probability? So who's heard the term random variable? Same group? OK. So for the purposes of this class, you just think of a random variable as, I know they're actually quite complex when you get into the real definitions of it, but you can just think of it as some random quantity, where basically it's some number that comes from some distribution, d. So the distribution could be, for example, it could be, take on value 1, the probability 1/2, and value 0, the probability 1/2, or something like this, right? There's some distribution over possible assignments to this variable. And we're going to use little p of z to denote its probability density. And so if when z in particular here is actually real value, we'll assume. We'll talk about regression here, though you can do the same kind of thing for classification. But assuming that z is real valued, then we're going to use p of z to denote its density. That's kind of like a distribution about where we expect the random variable to lie when we draw it. So there's a couple of things that we might care about this variable. And again, this is all very basic. I'm using kind of very imprecise language here, but hopefully the intuition comes through here. So there's a couple things we might care about this variable. The first one is its expected value, or mean. And the idea here is just that if we take a lot of samples of this variable and we average them all together, what do we expect that average to be? That's a little bit more formally defined as the integral over this density of the value of the variable itself. Don't worry about this if you haven't seen it before, but it's just the formal definition of what expected value is in this context. And I'm going to usually use the term mu to denote the expected value or the mean of a random variable. The other thing we might care about is the variance of a variable. And what this is the expected value of how much it deviates from its mean squared. So again, we take a bunch of variables, we just draw a lot of samples from this. These all have maybe different values. We draw all these samples. And then we subtract their mean and square that, and then take the average of that. And that is the variance of this variable. So if a variable, essentially, so give some intuition here. If this is P of Z, this density here, could be P of Z. This is a Gaussian distribution or something that looks like a Gaussian distribution. This, and say this is 0 here, then in some sense the height of this, or the sort of the little area in the very small region around here, would correspond to the probability that if we sample a random variable, it will lie somewhere in that region. That's what this area corresponds to. The mean in this case is, if we start sampling from a lot of these things, what will the average be? And that can be something like this. Say it's 0 mean random variable. And then on the other hand, the variance says, what the variance says is if I draw a random sample, take the difference between the mean and square that, what does that distribution look like? Or sorry, what's that number going to be like? Not the distribution, what's just the number of that thing. So for example, this distribution will have smaller variance than something like this. So both these distributions can have the same mean, assuming these are symmetric here. They're both sort of, when you average enough of these together, you'll still get 0 here. But the variance is much higher here because kind of what you expect is a lot of points all the way out here. And so subtracting them from the 0 value and then squaring that, you expect a higher value than you would for some density clustered around, kind of, or centered around 0 like that, more clustered around 0. Again, this is very, very high level, and if you haven't seen this before, I'm sure this probably is just equally confusing as this notation here. So there's a lot of references available, so please come chat if you haven't seen this before, just because it really probably is very important to have some basis in probability for machine learning, these kind of techniques. We're not going to be heavily focused on probability in this class, but having some intuition of these things is probably a good idea. So suppose now that we have m, and I'm going to use m again for the number of samples, and we have m samples drawn from this distribution D. And we write this as m z1 through zm is this little drawn from D. And this corresponds to just taking samples from this distribution, taking m of them. Now, as you might expect, remember the expected value, or the mean, is the expected value we would get if we take all those samples, or a very, very large number of samples, an infinite number really, and we average them together. So from some number of samples, 1 to m, we can estimate what that mean might be by just averaging out the different variables here, right? So we just form our estimate of the mean is just going to be 1 over m times the sum of all these different random variables here. And that I'm calling mu hat because it is an estimate, a prediction of what that mean really is. Similarly, we can also form an estimate of the variance of this distribution. Right? So if we take all these variables, we subtract their mean from them, say we know the true mean for a second, we subtract their true mean from them and square that, and then again average by m, that would be an estimate of the variance of this distribution. Right? And here, though, we're using the true mean. I'm saying this again, we subtract the true mean off. In practice, we might not know the true mean. So we can say, well, this is approximately equal to if we just subtract off our estimate of the true mean. And we call this now an estimate. And this last one here is now also an estimate of the variance. One thing you may have seen before is rather than the 1 over m term here, you may have seen a 1 over m minus 1 term for estimating the variance. If you've seen that, what that actually technically is a way of making this what's called an unbiased estimator of the variance. We're not going to worry about that here at all. They're very similar, obviously, for large enough values of m. These are going to be very close. It doesn't really matter that much whether you pick m or m minus 1. But essentially, that just corresponds to, do you want this estimator here, this estimate of variance here is an estimate of what we're trying to really measure, which is the true variance. If you want that estimator to have a property called unbiasedness, you have to, in fact, have this 1 over m minus 1 term. But it's a little bit less intuitive, so we're not going to use it for this class. We're just going to think about it as terms of 1 over m. So who here has seen things like this before? Sort of taking estimates and forming estimates using this kind of method. So are there any questions then? Because this is a little bit, this course is not at all about probability, but if you haven't seen it before, it might be a little bit confusing. So are there any questions about these estimates that we're forming here? OK, hopefully. All right, because it's going to get a little bit trickier now. So now let's get back to our two questions. Remember, our two questions were, what does the distribution of errors look like? And then how do we report some average loss in our final paper? So the first thing is, let's find out about this distribution, y minus y pred. So here I'm showing for that task of predicting, again, peak demand from temperature. You run the regression, and I forget actually which one I used. I think this was some RBF features with some lambda regularization or something like this. But the point is, and maybe I should actually go back a few slides. I'm going to flip through a lot right now, sorry. The point is that if you fit a line, and I don't even have the actual graph of fitting a line to it, but when you fit some function to this, look at the differences between those two things, and then plot a histogram of that. So you basically look at the different errors you get. How many errors fall into the range around negative 0.4, and then this height of this bucket here indicates how many errors fall into that bucket. This one here, how many errors fall into this bucket, etc., all the way up to the other side. So most errors, which is what you expect, and this is also on a testing set, I should mention, most errors, as you would expect, fall kind of into the range of zero error, right? Because otherwise you sort of could make things a lot better by just, say, adding a constant amount to your prediction, and that would actually do better, or subtracting a constant amount. So you really do want this to be somewhere centered around 0. If not, it kind of can be a lousy predictor. So this is what the histogram of these errors look like. Does everyone understand the significance of this figure here? Nods. OK. Now, we can treat these things, right? We can treat these errors here as samples from some distribution. And we can ask questions like, well, what's the mean of that distribution? Or what is the variance of that distribution? Right? And that's kind of what our goal there to do is we're trying to succinctly describe what this distribution looks like. Again, we might not be able to just giving numbers might not be a full description. If you really want to describe it, maybe you should just show this plot right here. But if we want some number that describes what this is, we can talk about what the variance is, or what the mean of this distribution is here. The mean is often called the bias of a distribution like this, because it's how much our prediction is biased away from kind of the actual 0 values that there should be. And then the variance is essentially, that would capture the fact that if you have a distribution like this, you're actually doing, in some sense, worse than if you had some distribution like this of your errors, right? Because this would be sort of, there'd be more errors that are closer to 0, whereas this one here would have a higher variance. So reporting these two things can be very useful for describing this actual distribution of errors here. Now, if in the case where you assume the errors are Gaussian, so assume, again, there's some reasons why this might be the case that things tend to Gaussian limit, but that actually doesn't even come close to always applying for this kind of data. But if we do assume it, well, actually, even if we don't assume they're Gaussian for now, we can just form our estimate of the covariance here by also assuming, if we just assume that there's zero mean. So if we just assume these things have zero mean, then the error here minus the mean is going to be just the error here. And so if we just take all these errors, square them, and then divide by m, that is an estimate of the variance of this distribution. Again, assuming that it's zero mean. If it's not zero mean, then again, we could probably make a better prediction by just adding some constant term to it. So ideally, this will be a zero mean distribution. And this term here should look familiar to you, right? It's actually just the mean squared error. So the significance of the mean squared error in some sense is that it also is an estimate of the variance of this distribution. And this is actually one justification for why you might want to use squared error as a loss function, for example. It is, in fact, assuming zero mean predictions, or zero mean errors, it is the variance of this distribution of errors. So that's point number one. That's sort of basically how we go about describing what this distribution kind of looks like. And for that, actually, mean squared error, even though it's also a loss function, ends up being kind of a nice description. And if you've seen something called root mean squared error before, that's just the square root of this thing. And that would just be, in the case of at least a Gaussian distribution, that would just be the standard deviation. Actually, no, sorry. In general distributions, it's still just the standard deviation of that distribution. And for a Gaussian, you have nice properties like about 66% of the data lie within one standard distribution. So giving these numbers give you some indication about where you expect your data might lie. Again, sometimes making assumptions like these things may look Gaussian or may not, but if you want to, you can also test those kind of assumptions as well. So that's all I'm going to say about this. This is essentially, all I'm pointing out here is that reporting something like mean squared error or root mean squared error, what you are effectively, and nothing else, if you just report that number, what you are reporting in some sense is kind of the variance of your distribution in errors. And that's kind of what you are doing by reporting mean squared error, for example. You're not taking into account here how much data you have or how confident you are in that. Because we're not talking about a confidence here at all, really, or some sort of average prediction. What we're really talking about is, of this distribution of errors, of this plot here, what is the variance of this distribution? So that's the first thing you can talk about, again, is what's this distribution look like? The next thing to talk about is if we want to report some mean error, which could be mean squared error, but it could be mean absolute error. It could be the sort of average deadband error, if you think that's more important. It could be really the average of any loss function. If you want to report that average loss function, how do you go about doing that? And here, we will come across the fact that as you get more data, you might be more confident in your reporting that average value. So now I'm going to show a different histogram, which looks very similar, but it's important. This is a slightly different thing. So now I am showing, before I was just showing the prediction minus y. So there were positive values, there were negative values. There were, it was just one was a prediction and one was the real thing, and the fact that it should be centered around 0. If instead we want to report the average loss, we can also draw a histogram of the actual loss function itself. So here I'm going to take absolute loss as my example, because I don't want to take squared loss, actually, just to make the point that this is not always the same thing as just looking at average squared loss. This histogram, of course, looks very similar because I'm just taking the absolute value here. So basically everything that was negative before just comes over to this side. But this is a different histogram. It's important to know, right? This is now a histogram of the loss itself, not of the differences between the output and the true value, the prediction and the true value. So, and if you average these things, it will have some mean that's kind of around here, right? It'll maybe be, the ones that are close to 0 count. There's maybe more of those, but you're also going to have some here. So this will not be 0 mean. In fact, that would mean if it was 0 mean, it means you have 0 average loss. So this is a different histogram here, and it's important to sort of, even though it's very similar in this case, it's representing a different thing. And now the question is, well, if we wanted to just take this loss, right, and average it. So we report, again, our performance equals, in our case, say 1 over m prime, the sum from I equals 1 to m prime of our loss function y hat I prime, yi hat prime. If we want to report that in a paper, how do we denote how confident we are in this prediction? And here we're going to exploit, again, a very, very simple version of the central limit theorem. So the central limit theorem says if you take a bunch of samples from a distribution and average those samples together, that's sort of like drawing a sample from another distribution, right? The average is itself a random variable because you've created from random variables a new one. And you can keep doing that, right? You can draw a bunch of samples, average them, get one sample, draw another bunch of samples, average them, get another sample. And what is the distribution of that new, what is the distribution of that new sampling? Or what is the density, I guess, of that new distribution that you're sampling from? What the central limit theorem says, and with some conditions here that I'm not mentioning, but it's sort of treated as kind of fact by a lot of people or in a lot of situations, is that the distribution of these averaged values, regardless of what their distribution is, so the average values could have whatever distribution they want. The initial samples can have whatever distribution they want. Central limit theorem says when you average them together and treat that as a random sample, that new distribution tends toward a Gaussian, a normal distribution, with mean equal to the mean of the original distribution and variance equal to the variance of the original distribution divided by the number, that should be m, divided by the number of samples m. So have people seen this before? Does that make sense? Because that's kind of a mouthful, but it's very important to see what's happening here. You're taking random samples, you're averaging them together. It doesn't matter what distribution those are. So this distribution here is nothing like a Gaussian at all, right? It's very, very unlike a Gaussian, in fact, because it's never negative. It's clipped there. What I'm saying is, if I average these things together, that distribution will tend towards a Gaussian, kind of regardless of what this distribution actually is. So this is a nice fact because for Gaussians, we have this very nice property that, for example, if you, and so people here are familiar with Gaussians in general, right? Who here has not heard of a Gaussian distribution before or hasn't used them, ever seen them before? Just by a show of hands. So we can chat afterwards. I can maybe explain this in a little bit more detail. But basically, there's some distribution that has a density that looks like this, right? And with this is the mean. And 95% of this area here lies within about 2 standard deviations away from the mean. So if this term here is sigma, and not sigma squared, but just sigma, about 95% of the data lies within 2 of these things. So this area is 95%. This here is 2 sigma. So this is a nice thing because we know things lie within 2 standard deviations. And again, this should really be m here. You're dividing by the number of samples you've averaged over. This is a nice thing because if you take a bunch of samples from any distribution and you average them together, you know that their mean lies with 95, again, I'm using probabilities here very, very loosely in a way that would probably make a lot of people crazy, but forgive me for that. The true mean in some, so you take a bunch of variables, you average them together to get some estimate of what their mean is. This theorem says that the true mean, the true actual average of those things, drawn at random from D, lies within, say, 1.96 standard deviations 95% of the time. So you can then say what, in some sense, actually, I'll just put this next slide here. This suggests a method of kind of reporting a kind of confidence interval for your estimates, right? So what you do is you take your loss function, and I'm going to call this now mu, because it's an estimate of the mean value of these losses here. That can have kind of a lot of different types of distributions, but we can also form an estimate of the variance, not of this loss itself, but an estimate of the variance of this actual mean estimate. So our variance estimate, or actually maybe I should say, the variance estimate of the actual random variables themselves would just be the standard estimate of the variance we saw before. So that would just be 1 over m prime, sum of I equals 1 to m prime. This thing, the loss, y hat prime I, yi prime, minus our estimated mean. That would be our estimate of the variance of this distribution. The distribution of losses, that is. But now we can say that, again, with 95% confidence, very much putting that bit in quotes here, the true mean lies within our estimate mu hat plus or minus 1.96 sigma. That's the rule for a Gaussian. But remember, this is the variance of our means. Our variance of the losses. If we want to know where the true mean lies, the variance for that thing is this Gaussian where the variance is divided by m.
One question.
Yeah.
So the mean, the mu and the sigma square is known or unknown?
These are both unknown here. You don't know the variance or the mean of your losses. That's what you're trying to report.
Okay.
Okay?
They are parameters that we would want to compute.
I mean, I wouldn't call them parameters because I use that term kind of for like parameters of a model here. These are just estimates you want to form from your data, right? They're unknown. Mu is the mean of your losses. Sigma squared here is the variance of the losses. And what you report in the final thing is mu plus or minus 1.96 sigma, importantly, divided by the square root of m prime. And this is known as a 95% confidence interval. And what we're saying here is we're not saying that if you draw some random loss, that will lie within mu plus or minus this thing. Right? That would be very hard to say because A, it's false. You don't know what distribution this is at all. The losses can come from any distribution, probably not a Gaussian. So you can't even say this for the variance here without this over square root of m term. But what we are saying is that the true mean, so if we repeat this process a lot of times, the true mean of these things is going to lie within our estimated mean plus or minus this term here. And the reason we can divide by m here is from the central limit theorem, right? As we get a bigger sample size, the variance of our actual mean estimate goes down, like the variance of the original samples divided by m. And so in this case, what this corresponds to is saying our means, if we look at that distribution, that is a distribution with this same mean here, or on average the same mean here. And the variance of that distribution of means here is going to be sigma squared over m. So again, using the Gaussian property now, we say that 95% of the time this falls within this range. And if that was a little bit confusing, you can come chat. Happy to explain it a little bit more. But in general, this is just kind of a process you can follow that will give you a way to compute how confident you are in your estimate. Now, those that might know the subject a little bit more know that this is actually not quite a correct procedure here for a few reasons. First of all, we probably shouldn't be using this estimate of the variance. We probably should be using that estimate that had the m minus 1 term there. That would be a little bit more fair estimate of the variance. So it would be a little bigger estimate of the variance. And secondly, these things, we shouldn't actually be using a Gaussian distribution here. For technical reasons, because we don't know the mean ahead of time, we actually should be using what's called a student t-distribution, which is like a Gaussian, but for small data, it's a little bit, has fatter tails. For low amounts of, for low m here, it has kind of more probability mass away from it. What that corresponds to is saying you actually need a bigger constant here than 1.96. You'll need a bigger constant there, which you can get from the student t-distribution. But again, for large samples, this is a very good approximation to that student t-distribution and to the right thing here. So essentially, this procedure for reasonable size m will give you things very reasonable as a 95% confidence interval.
So, for example, if the number of samples is not very big, relatively small,
yep.
can we just repeat the whole process and using the student t-distribution?
I don't think that's quite what you would want to do. So there are other ways you can report errors. And when you start talking about repeating things, so drawing many test sets and training sets, it gets a little bit trickier how you report those things. This is really a procedure for you have some training set, you have a test set. And your test set is of size m, or m prime here. Obviously, depending on the size of your test set, you might want to report a different confidence in how sure you are of that estimate. Now, you might say that, well, if I repeat things a lot, I might be more confident in it. But that confidence is actually limited by your ultimate size of your total data set, right? If you only have, say, 10 total examples, you still don't want to really say that you're super confident in it. So there are other strategies you can use for a situation where you want to repeat this experiment many times. This really, and we won't get into those here, but there are other things they're called things like the bootstrap and stuff like this. There are other methods for doing things like that. This method here is really about if you have a fixed test set and you have some loss you're averaging over that, you want to report that average loss, and you just want to say how confident are you in that. And that here is just kind of the rule for how you go about doing that. And as you would expect, with more data, this thing, square root of m, gets bigger, and so your confidence interval therefore gets smaller. So with lots of data, you have a very small confidence interval, and with very little data, you're not dividing by very much here, so you have a very big confidence interval. And in fact, with very, very little data, this is actually a very bad approximation to the student t-distribution, and so you probably shouldn't use it at all. But for 30 or so examples, this starts being pretty good. So if you have that many examples, you can use this without anyone faulting you too much. But it's important to know sort of what we're reporting here as the confidence interval. We're reporting our confidence interval of the mean estimate, not of the loss itself. So we're not saying the loss lies within a certain range. We're saying the average loss lies within a certain range. That's a very different statement. You can't really say much at all about where the loss lies, other than the things I said before about maybe plotting that histogram or something like that. But the average loss you can say a lot more about. Now, this also doesn't always work correctly. So for things like classification tasks, for example, where it's sort of almost holds, but when you have very high accuracy or very low accuracy, for example, these sort of theorems actually don't kind of start breaking down a little bit, so you might not always want to do those there. There are equivalents you can do for classification tasks. But even for classification, this actually can work okay in a lot of cases. This still gives you reasonable estimates of the errors involved. So again, if some of the math here was a little bit confusing, just remember this is sort of how you go about reporting what your average loss is on a data set of size m prime. And finally, one thing I should say is that, and the other thing is that it's really good to report errors relative to some baseline too. If you just say, my performance on predicting peak demand is I have an average, this is actually average mean squared error. So I have an average mean squared error for the degree 3 polynomial of 0.12. So I guess here would be 0.12 degrees because you're talking about mean squared error, right? Sorry, mean absolute error here. This is this plot that was, again, before showing the average error on a test set as a function of different degree polynomials. So if you want to know, say, what degree polynomial to pick, or which ones, how each of them perform, you might want to either report this if on a test set, if you're trying to report the errors, or maybe do something like this on a cross-validation set if you're trying to pick which degree of polynomial to use. But it's very important to report or compare it relative to some baseline. So for example, a 0-degree polynomial would just be approximating everything with a constant. And that is a much better baseline than, say, predicting everything to be 0. Especially if your data lies, there's very few days with 0 electrical demand. So if you compare to predicting 0 all the time, that's going to be a very bad comparison. Versus comparing to predicting just the mean, which corresponds to a degree 0 polynomial, that would be a much better comparison. And what we see here is that this table here shows the mean average absolute error, and then plus a 95% confidence interval. And what you see here is that you can say that because these two, for example, degree 0 and degree 3, those clearly are not overlapping, those two confidence intervals there, right? So clearly, or at least with some probability, again, I want to use that term very, very loosely because I'm not really talking about probabilities here, but with some confidence, you can say that 3 is in some sense a better estimator than a degree 0 polynomial, degree 3 polynomial. On the other hand, you have some terms like a degree 3 polynomial and a degree 4 polynomial, where 3 actually is a little bit better than 4. However, in this case, those confidence intervals are overlapping, so we can't say with confidence, actually, that 3 is definitely a better predictor than 4. We would actually need more data if we were going to say that with some confidence. And so giving confidence intervals like this is sort of a crude way of getting some estimate of whether or not there is statistical significance in your predictions. So if you have two predictions here, say method 1, actually I think I would be cut off there. So sometimes what you'll see a lot in some plots are things like this, where they have method 1, and this is again performance in unknown units. Method 1 has some performance like this, and then error bar looks like this. So people often draw them like this on charts. And then method 2 has a little better performance, but maybe the error bar is overlapping, or in fact the mean here even lies within that other error bar. It'd be hard to say that one was definitely better than the other. On the other hand, if you have same results, same means, but very, very small intervals, i.e. you've used a lot more data, or the variance of your predictions is a lot lower, the variance of these losses was a lot lower, then you could say with some confidence that these were actually, one was better than the other. Now, the last thing I want to mention is this is not the best way to compare algorithms. But it's a much better method called hypothesis testing. And the idea here is that we're taking averages. So it could be that on every single example in your set, method 1 performs worse than method 2. It's just that there is a lot of variance in their performance. But still, method 2 is always better than method 1. In this case, you still want some way of saying, well, even though there's a high variance in these losses, there should be some way in which we can say, well, method 2 is still better because it still always has lower loss, say, than method 1. And you can do this. It typically goes by the name of pairwise hypothesis testing. You essentially do things like look at the distribution of the differences of these two things, but we won't get into that. Just know that if you have seen these things before. There are better ways of reporting errors than error bars, but error bars are very nice. They're very visual. I mean, if you have lots of different methods here, it's not always easy to draw always easy to draw hypothesis tests on a graph, whereas confidence intervals are kind of a nice way of drawing these things and serve as a pretty good initial estimate of how good algorithms perform and how confident you are in that performance. All right, so does that all make sense? That is the last bit on machine learning, though we will use machine learning a lot, especially when we start talking about control tasks. We're going to actually kind of revisit a lot of these things and talk about machine learning for making temporal predictions. So we talked here about making a prediction for a given day. What will the temperature be like tomorrow? But all we used in some sense was what will the peak demand be tomorrow? But all we used for that was the high temperature, right, to make that prediction. We didn't really use, well, what was the peak demand yesterday? When you start talking about tasks that you want to control and things where you want to actually make decisions in the future given what you've seen in the past, a very useful thing to use is to be able to make predictions given past data about what the future will look like. And this goes with the name of things like autoregressive models and things like this. We'll revisit those when we talk about control, but for the time being, we're going to just focus on, or close out machine learning when we talk about this, and then revisit machine learning again when we talk about control. But this ends the unit on machine learning, the mini unit on machine learning, and let's see how much time I have left. Okay, so I probably won't get to the power system stuff today. We'll get to that next time. But in the last 20 minutes or so, I just want to give a very brief description of another possible application of machine learning methods. So this was a conference paper that I had with someone at MIT a few years ago. And does not work. Oh, no, it's here. Sorry. Wrong button. OK. So this is some work I did with predicting energy consumption in buildings. And these are the conference slides. So I'm actually presenting that way intentionally because the idea here is hopefully that after going through this course, or at least so far the course, things like this will make a lot more sense. And so presentations about machine learning methods will hopefully make much more sense. And you'll see that we really didn't do anything very complicated here at all. We were just applying machine learning methods, the ones you've already learned, to a task like this. And this was a nice conference paper. Got a lot of interest in it. So in some sense, what this means is that what's interesting in these papers isn't the methods, it's the data itself and the conclusions you make from the data. But really, everything we're going to present here, you will understand perfectly well. So, I think the motivation here is that, and I'll skip through this fast because it's sort of little cartoons I had for this conference itself. But the motivation here is that, if you want to say retrofit your home, or if you are a company that retrofits homes, you might have a hard time, right? Because you don't really know which buildings to target in an entire neighborhood. So you just see a bunch of buildings and you say, well, which home should I actually go to put in more insulation? Okay, or suppose you're actually a homeowner here and you want to outfit your home, or you want to be more efficient in your home, so you're going to install some bulbs or something like that. But it's also very hard for you to really know what parts of your home to address, right? Because you don't really know, when you get your bill every month, you don't really know, well, is this good or bad? Can I really do that much better or that much worse by doing all these upgrades to my house? And the fundamental problem here is that it's very hard to put energy consumption into context, right? So if we get a bill from someone, if we're like a retrofit company and we get a bill from someone, it's very hard for us to know, well, is that good or not? Are they going to be able to save a lot of money and energy by retrofitting their home, or are they not going to be able to? Maybe they have a very well-insulated home, it's just a very big home. It's hard to kind of know these things. And similarly, if we get our energy bill, we don't really know, well, is this really good or bad? Am I using a lot of energy or a little energy? I don't know if that's the case. And so the goal of this work here was to take a lot of publicly available features that would describe buildings, right? Things like square footage of the building, the type of building, is it commercial or residential, the value of the building, maybe the actual monetary value of it, and use these to predict what do we expect their gas and electricity consumption will be on their monthly bill. And the usefulness of this in some sense is not that we're going to be able to get this exactly right, because we're not, of course, going to be able to predict everyone's bill exactly. But the value here is that if we actually can construct some kind of distribution over expected consumption, we might be able to then say, well, if you lie, maybe if you are using this much energy, 145 kilowatt hours, maybe you lie on sort of the upper range here, and you're using a lot of energy, versus maybe if you use a little bit, you're actually doing quite well. And we want to customize this to the actual what we would expect from your home, given all the features of it, right? Because it's not really fair to compare a great big home or a commercial building with a residential home or a smaller home. And that's the basic idea here. So there's lots of related work. I won't go into this because this is, if anyone's curious about this, like for a project, by the way, things like this can make great projects. So if you want to learn more about this kind of work, there are also companies that should add doing this. People like O-Power are building systems like this that actually do tell you how you compare to your neighbors. They don't really describe how they do it, but there are companies out there doing things like this. So the key point, I guess, in some sense, is that this work itself, the machine learning was not anything new. I mean, we're using just well-known methods. The key ideas were a couple ones, which I'll highlight in a second. But in some sense, what was really nice about this is we actually got access to monthly gas and electric bills for every home and building in Cambridge. So that's where I was up until this year. And we got, once we sort of correlated all the things and we processed it, it was about 6,500 total buildings in Cambridge, for which we had the monthly bill. We had from tax assessor records things like their living area, their building value, was it residential, commercial, the occupancy, etc. And there were about 35 different features in total that we were able to compute for these different homes. And so at this point, we can actually start plotting what these things look like. And so, well, what do you know, one thing I actually encourage everyone to do is that before you start just throwing every machine learning algorithm you can at a problem, just plot the data first and see what it looks like. So what does this actually look like here? So as you might expect, things like energy consumption do depend on things like living area, of course, because a bigger home will tend to consume more energy. And this plot now shows the building living area in square feet and energy consumption on the y-axis. Now, the interesting thing about this plot here is this is a log-log plot. So both axes here are logarithmic. And that was really surprising to us when we first saw this, right? Because you think of, oh, you know, one home's going to use 10% more energy than another, etc. What the data actually showed here was that although there is definitely some correlation here, so clearly homes that are bigger use more energy, even for a given size home, so say just look at homes that are 2,000 square feet, there is still a huge distribution over possible total monthly energy consumption for these homes. This is a logarithmic scale, remember. So some homes use 10 times as much as other homes. And that's kind of the scale you would imagine, not things like 10% more, but really 10 times more than other homes. So that was really surprising to us. But this motivates kind of the type of algorithms we apply, right? Because if you weren't now to look at log space, data would essentially be all scrunched down to the axis. You couldn't even really see it, and there would be a few outliers lying, you know, at certain points. And so when we talk about fitting models to data, it's much better actually to fit models in this logarithmic space than it is to fit models in the original sort of space where you treat energy consumption just as a number itself without taking the logarithm of it first. And just to actually give us an idea, here's what 10 100-watt light bulbs would look like. That's that line right there. So, you know, this is about how much energy homes use. OK, so we can also plot this kind of, you know, just a histogram, as I showed before, of total consumption or average consumption per the year, and the number of homes that do it. And as you can see, it kind of looks like a normal distribution, but on a logarithmic scale. So actually not normal at all. It's log normal in some sense. So at this point, we just apply our machine learning methods, right? So this is exactly what we were doing in this class here. I'm framing it in a little bit more probabilistic way. So I'm just saying that we're going to predict the log of the energy as maybe a linear function of some features. Or in the kernel version, we're going to do it as a linear function of some kernels, right? So we're going to either do it in the original feature space or in this kernel space. And then we're going to also add some noise term. And that noise term really is just the same as having a loss function. So basically, we're saying this equals that plus some noise. Or you could also just say, let's just then therefore minimize this minus that, where the distribution of the noise term determines which kind of loss function you want to use. And the second element, so the first kind of trick was that we do want to really predict this log of the energy, not just the total energy itself. Second trick was we actually want to use non-Gaussian noise terms. So we didn't talk about this too much in the class, but essentially least squares can be derived as this model with a Gaussian noise term, or a Gaussian likelihood it's called. Whereas something like using the absolute loss can be derived as this same model with a different distribution of noise. In the case of absolute loss, it's called a Laplacian noise distribution. And another big insight here was that different distributions here, or in our case, just different loss functions, actually change the predictions quite a bit and will make them work a lot better in some cases than others. So again, these sort of two key insights. And this is really the only kind of novel elements of the paper other than getting the data set and running these experiments. The novel elements were, from the data, we got the fact that there was interesting structure in this logarithmic space rather than the original space itself. And then, again, from the data, we started finding that non-squared loss functions, so things besides least squares, actually will make these things perform a lot better in some cases and give you a better estimate of probabilities. Now, I'm going to report the performance of methods in terms of their log likelihood, which is something we didn't really cover. Basically, just know that higher is better under this metric we're talking about here. So if we just model the energy, this is just predicting the mean energy, essentially very home, we get some log likelihood. If we use linear regression with a Gaussian likelihood, meaning least squares regression, we get a little bit better. If we use a student t likelihood, we actually do a little bit better, which is a little bit different distribution, a different loss function, essentially. If we use a Gaussian process, which is just kernel linear regression, actually. You might have heard the term Gaussian processes before. That is just kernelized linear regression is all it really is. It does a little bit better. And just to show, if we don't take these logs here, we do much, much worse than everything. So, yes, question?
What's the loss function for the student t likelihood?
It's a little bit complex because it's actually not convex. It has to do, there are two parameters. There's a degrees of freedom parameter and the variance type parameter. And they both enter it. I actually forget the exact form right now, that we could look it up, or you can look it up on Wikipedia and see it. It just looks like a Gaussian, but it actually can be spread out more by decreasing the degrees of freedom parameter.
So it just has fatter tails?
Yeah, has fatter tails than the Gaussian, yeah. But it still looks kind of bell-shaped still. And though I'm not showing it here, again, not following my own advice in terms of reporting error bars here, what we did instead was this hypothesis testing. So these actually aren't quite, you can't quite separate these out just with error bars. So instead we did hypothesis testing to show that this is in fact statistically better than the other ones with some p-value that's less than whatever people determine to be the appropriate one for determining significance. Okay, and I guess one way of describing this is that the variance of our predictions decreases by about 75% if we include all the features in it, versus if we just try to predict the mean of the distribution, for example. So this is talking about now actually the distribution of errors, and we're saying that we can decrease that by about 75% if we add all these other features, and so we condition all the other features. And what I think the effect that's saying is that we can explain a lot about energy consumption using just publicly available features of a home, like square footage, like the value of the home, etc. Which makes perfect sense, right? You would think, of course, the power consumption would be correlated with those things, but this kind of was a nice study that showed that, in fact, can make those types of claims. The next bit was kind of a fun bit here, and this is saying, okay, so we have these features. This is something we didn't talk about too much here. I just want to make sure I'm okay in time. So I'll probably end after this. I won't show the last little bits. But if we talk about now, we haven't really talked about this too much, but one thing you can ask, we talked about a little bit in terms of polynomial features, for example, but if you have some fixed set of features, one question you might want to ask is, well, which of those are you actually using to make your prediction, right? Or fixed set of inputs, I guess is the way we've been talking about it. Fixed set of inputs, which actually end up being the most relevant for your prediction. You know, maybe you include the temperature of something completely unrelated, right? Some temperature in Florida for what they're going to consume per month in Cambridge. That's probably not going to be a very relevant feature for your prediction task. And there'll be a lot of things that seem like they might be related, like, say, the number of bathrooms in a home. It's one thing we have. Didn't end up really affecting our prediction at all. So what we can do is actually look at which inputs should we add to most increase the predictive ability of our algorithm. Starting out with none, you might want to add one and see how it improves, and try them all and add the best one, maybe. This is a procedure called greedy forward selection. And it's not, I should add, the best way of coming up with features, but it's really not that bad either. It works well in a lot of cases, just picking features one at a time, depending on which is the best one. So we have all these features. We have things like square footage of the home. We have things like the year it was built, number of occupants, the value of the home. And the question is, which of these ends up being the most relevant? Does anyone have any guesses about which one would be the most predictive of how much energy a home will consume? Commercial versus residential, all these kind of things. Guesses, throw out. I mentioned a few. Are there any guesses?
Size.
Size, yeah, that's what I thought it would be too.
Number of occupants.
So occupants, that would be a good guess also. So actually, it turned out the most expressive feature was the building value, according to assessor records. And it was positively correlated. So even if you add square footage, for example, it still actually is better just to add the actual cost of the home, according to the tax assessor records. And it kind of makes sense, but it's a little bit sad too, right? It says basically if homes that are more expensive use more energy, at least in Cambridge. And that's, you sort of would hope for the opposite, right? Maybe homes that are more valuable do a better job insulating, so they don't use as much energy. That wasn't the case here. More valuable homes, they just start using more and more power. So there are a couple things you can do with this, like you can develop tools that will show you this graph here. So actually this graph was in or this plot here was on the course webpage. What it was a map of the city showing how houses compared to what we'd expect them to do. So look at their expected consumption, and we plotted them as being red or green based on how good they actually were. Now this is actually not the real graph. We can't show that because there's privacy concerns. But the real graph looks pretty much just like this. Do buildings consume more or less power? And we code them as being good homes or bad homes. And someone like a retrofit outfit now could use this to say, well, these homes are the ones using a lot more power than they should, given what we know about them. Let's target those ones to sort of do these things. And you could also have a system where you actually input your own bill, and it tells you where you basically land in this setting. So again, the point of all of this is that this is just an example of one thing you can do with methods like machine learning. There's nothing new in the machine learning side in this whole paper here. It's just using standard algorithms, ones you've learned, in fact. It's using linear regression and kernel linear regression with different loss functions. And that's all it was doing. And from just that, you're able to develop these tools, which are actually very useful, not just, probably not to machine learning people, because they wouldn't necessarily care about just more or maybe they would like the fact that it works well in an example. But for someone like a retrofitter, you build a tool that would be very useful for them using these techniques for machine learning. So that's the basic idea there. We're going to, again, have more office hours tomorrow. I'll send an email out about that time. I'll also post the project descriptions today on the website. And then on Thursday, we will talk about power and start talking about AC and DC circuits. Great.
What is it after